Hi everyone, welcome to Nexus of Thought. Today I want to talk about the electric field between parallel plates, which are also known as capacitors. So here we have a parallel plate arrangement over here. The top plate is positive and the bottom plate is negative, and we've charged it positive and negative by establishing a potential difference between the two plates. The arrows represent the direction of the electric field, which points from the positive plate to the negative plate. And the little red lines, I'm getting colorblind here, the little red lines actually represent what's called the potential gradient between the plates. We'll talk a little bit about that later. So if you place a positive charge between these plates, it will get driven to the negative plate with a force of QE. So the force on the charge would be equal to QE. And if it's a negative charge, it will get driven to the positive plate. The key thing to remember is that a force will exist on the charge. This force is uniform, as the electric field between parallel plates is uniform. And the driving force is the potential difference between the two plates. And that, of course, is maintained by the power source. So what we're going to look at now is how can we analyze this particular problem using conservation of energy. So in this situation over here, I have two plates. One is at 100 volts and the other one is at 0 volts. So for all intent and purposes, we can treat the 100-volt plate as the positive and the 0 volt as a negative plate because it's at a lower potential. The green line over here represents an equipotential line. That's the potential is the same throughout. So it's 75, halfway in between it's 50, and then here it's 25. So you can see there's a gradient going from 100, 75, 50, 25, all the way to 0 volts. Now suppose we have a little, this plate has got a potential 100 volts, and we say it's V1, and this one is going to be V2. Now what we do is we place a little test charge next to the plate over here. It's a positive test charge. What's going to happen is that this particular positive test charge is now at a high electric potential. So it's very similar to if you have a object and you're holding it up in the air. It has a lot of gravitational potential energy, and it wants to actually fall. Well, the same thing is true of the positive charge. It wants to actually move towards the negative plate. So here it has a high electric potential energy and it wants to move to the negative plate. As it moves, it converts that electric potential energy into kinetic energy. And that manifests itself in a change of speed. So that's what's happening. It moves, it converts the electric potential energy into kinetic energy. And then when it hits the negative plate, it will actually have converted all its electric potential energy to kinetic energy. So we can actually make use of conservation of energy to solve this problem. We can say that the electric potential energy at plate 1, which is this guy, plus the kinetic energy at that plate, which is EK1, is equal to the sum of the two energies at the second plate. Now, if you start from rest, EK1 will be equal to 0. And at this plate, if we make this the reference plate, then we can make that EE2 0. So what you can actually do then is you can say that the EE1, the electric potential energy at plate 1, is equal to the kinetic energy at plate 2. And from that, you can actually solve for the speed of the charge. Another way of looking at the same idea is to say that the change in electric potential energy is equal to negative the change in the kinetic energy. Or one way of looking at it is to say that whatever energy is lost, electric potential energy wise, it doesn't get lost from the universe. It actually gets converted into kinetic energy. All right, so there's conservation of energy that you can look at there as well. The other idea which comes from the parallel place, and I have to thank Physics Ninja for this really great diagram over here, is the concept of the way in which we can actually look at the electric field between parallel plates and come up with a really neat equation. It's called the derivation. It's called what I'm doing here is deriving the parallel plate equation. So I'm using squiggly E to symbolize your electric field. And it's equal to negative the potential difference between the two plates divided by delta D, which is the charge separation. So here's an example. Let's say we've got a charge which starts off at the negative plate over there, and we want to actually move the charge towards this positive plate over here. And notice that the potential gradient, here it's low, there's high, runs opposite to the direction of the electric field. The electric field in this case is 10,000 newtons per coulomb. These are just a few values to make it seem a bit more practical. So where does this neat equation come from? Where does this electric field equation come from? Well, we can make use of what's called the work potential energy theorem. And the work potential energy theorem says that the work done by the electrostatic force is negative the change in the electric potential energy. So it's the same as gravity. So if the charge is moving in this direction, then the force of repulsion will be in the opposite direction. So the force of repulsion is like this, the displacement is like that. So you're going to a higher electric potential energy, but it's doing negative work. It's doing negative work. So that's why you have to have a negative sign over there. So what we're saying is the work done by the electrostatic force is the force Fe times delta D. All right. The angle is actually, in this case, cos 180, but we won't worry about that now because we were just using the formula. And that is equal to negative the change in the electric potential energy. So it's negative EE2 minus EE1. Now we already know that Fe is equal to QE. So this, we can substitute QE, this is squiggly E, we can substitute that in for Fe. So you're going to have Q squiggly E delta D, and that's going to be negative QV2 minus QV1. Don't forget that QV is just equivalent to electric potential energy. So we're going to have that. Now, the one thing you can do is you can cancel out the Q's. So you're going to get something like this. Your electric field times delta D, which is the displacement or the separation between the two plates, is minus your potential at your top plate plus the potential at the bottom plate. It looks like that because there was a minus sign in front of it. So rearranging for all of this, we see that your electric field, which is squiggly E, is equal to minus delta V over delta D. All right. And the minus sign, of course, just indicates that the electric field points in the opposite direction to the electric potential gradient. And that's an important note. So this equation over here, which is the parallel plate equation, is very, very useful for dealing with these type of problems between parallel plates. But there's an important caveat that you have to remember. And the important caveat that you have to remember is that it only works if the electric field is uniform, which is fine for parallel plates. But if you got just a single charge and I ask you what is the electric field at a certain distance from that single charge, you cannot use this equation because the electric field drops off with distance from a single source charge. So you'd have to use the older equation we derived, which is E is equal to K, Q being the source charge, divided by R squared. Okay, so and just remember that delta V, of course, is your potential gradient. Now, what's kind of neat here is that thrown up from this equation, you can see that we can also use the units volts per meter to represent the electric field. And for those people who want to try, you'll see that it's dimensionally equivalent to newtons per coulomb. All right, so that's a little bit of an introduction into electric fields between parallel plates. If you like this video, please give it a tick a hands up, make a positive comment, and if you feel it's good, subscribe. I appreciate it, and I plan to make more of these in the future. Thank you. Bye.